something just happened that has astronomers around the world on edge. On October 3, 2025, an object from another star system passed within 30 million kilometers of Mars. That might sound like a huge distance, but in cosmic terms it's practically a close shave. And here's where things get weird. This visitor, known as 3I Atlas, didn't just randomly swing by the red planet. New findings suggest this encounter might not be the coincidence scientists initially thought it was. When 3I Atlas was first detected back in July, astronomers figured it was just another icy wanderer from the depths of space, following the laws of gravity through our solar system. But the closer researchers looked, the more uncomfortable they became. This thing is heading straight for Mars with a precision that's raising eyebrows across the scientific community. And the latest data is making some experts question whether we're dealing with something entirely natural at all. What makes this Mars flyby so concerning is the composition of 3I Atlas itself. Recent spectroscopic analysis revealed something that sent chills through research teams. This interstellar visitor is wrapped in a thick fog of carbon dioxide, not water vapor like most comets, not hydrogen or methane, carbon dioxide, the exact same gas that dominates Mars's atmosphere at 95%. Think about that for a second. An object travels thousands of years through the void of interstellar space, arrives in our solar system, and just happens to be made of the same stuff as the one planet it's passing closest to. The timing couldn't be more perfect either. 3I Atlas made its approach when Mars was positioned in a way that allowed every major space telescope and Martian orbiter to observe the encounter. ESA's Mars Express and the ExoMars Trace Gas Orbiter were already in position, giving scientists a front-row seat to whatever was about to happen. It's almost as if someone planned this entire event to be witnessed and studied. Some researchers are calling it the astronomical event of the decade. Others are quietly wondering if it's something more deliberate. But the Mars connection goes deeper than just chemistry and trajectory. Scientists have started noticing behavioral patterns in 3I Atlas that don't match any comet we've studied before. As it approached the red planet, instruments detected unusual electromagnetic signatures emanating from its core. Radio telescopes picked up faint but structured emissions that some describe as almost rhythmic. When asked about these signals during a recent press conference, a NASA spokesperson stated they were still analyzing the data, but admitted the patterns were unexpected and worthy of further investigation. The statistical probability of all these factors aligning by pure chance is astronomically low. An interstellar object showing up with Mars-like composition, passing at optimal viewing distance during perfect orbital positioning, while exhibiting unexplained signals. One astrophysicist put it bluntly in a recent interview, stating that if you calculate the odds of these coincidences happening naturally, you'd be looking at millions to one against. Yet here we are watching it unfold in real time. Before we dive deeper into the Mars mystery, you need to understand just how bizarre 3I Atlas really is. This isn't your typical comet, and it's not behaving like the previous interstellar visitors we've encountered. In fact, recent measurements have revealed something that has scientists scrambling to rewrite their calculations. This object is massive. Not just big, anomalously massive. That's the exact term researchers are using. And in the world of astronomy, when scientists say something is anomalous, it means it doesn't fit any model or theory they currently have. Initial estimates suggested 3I Atlas might weigh a few million tons, similar in mass to other large comets. Those estimates were dead wrong. Updated calculations based on gravitational influence and outgassing rates now put the mass at over 33 billion tons. Let that sink in. 33 billion tons of material that somehow formed in another star system and made the journey here intact. To put that in perspective, it's roughly 1,000 times more massive than any comet previously observed passing through our solar system. The sheer size challenges everything we understand about how objects are ejected from planetary systems and survive the journey through interstellar space. Here's where it gets even stranger. That carbon dioxide fog we mentioned earlier, it's not behaving the way it should. When comets approach the sun, they heat up and release gases in predictable patterns based on their composition and size. Scientists can calculate exactly how much mass a comet should lose and how that affects its trajectory. But 3I Atlas is defying these calculations. It's shedding carbon dioxide at rates that suggest it should be much smaller than observations indicate. Either our understanding of cometary physics is fundamentally flawed, or something else is going on beneath that dusty exterior. The composition itself raises questions that make veteran astronomers uncomfortable. Most comets are pristine time capsules from the early solar system, packed with water ice, frozen gases, and primordial dust. They form in the cold outer regions of star systems where water is abundant. But 3I Atlas appears to have formed in an environment more similar to the inner regions of a planetary system, where carbon dioxide would be more prevalent than water. That's the kind of place you'd find rocky planets like Mars, not icy comets. So what was this thing doing in an environment like that, and how did it get kicked out into interstellar space? Spectroscopic analysis has detected other unusual signatures as well. The object is emitting cyanide gas, which isn't uncommon in comets, but the concentrations are far higher than expected. Even more puzzling, instruments have picked up atomic nickel vapor in the surrounding cloud. Nickel, that's a heavy metal that requires significant heat to vaporize. The sunlight hitting 3I Atlas at its current distance shouldn't be nearly hot enough to produce nickel vapor from rock. Yet there it is, glowing in the spectral data, defying conventional explanation. Some researchers have suggested that 3I Atlas might not be a comet at all, but rather a fragment of a destroyed planet from another star system. This would explain the unusual composition, the massive size, and the carbon dioxide dominance. Imagine a rocky world, similar to Mars, that suffered some catastrophic event billions of years ago. Maybe it was shattered by a collision with another planet, or torn apart by tidal forces when it wandered too close to its star. Chunks of that world would have been flung into the darkness of interstellar space, carrying with them the chemical fingerprint of their origin. If that's what 3I Atlas is, then it's not just a visitor from another star system. It's a piece of an alien world, possibly one that once harbored conditions similar to Mars. But there's another theory making rounds in certain scientific circles, one that's far more controversial. Harvard astrophysicist Loeb has been vocal about the possibility that 3I Atlas could be artificial. Loeb gained fame and criticism for suggesting that Oumuamua, the first interstellar visitor, might have been an alien probe. Now he's raising similar questions about 3I Atlas, and this time, he's not alone. A growing number of researchers are admitting, at least privately, that some of the data doesn't fit natural explanations. The Mars encounter, the unusual composition, the anomalous mass, the unexplained emissions. Individually, each could be explained away, but together, they form a pattern that's hard to ignore. The story of 3I Atlas begins on a routine night in July 2025, when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, picked up a faint smudge moving across the sky. At first, it looked like any other distant comet, barely visible even to powerful telescopes. The automated system flagged it for further observation, and astronomers began tracking its path. Within days, they realized something was off. This object wasn't following an elliptical orbit around the Sun like comets born in our solar system. Instead, it was moving in a hyperbolic trajectory, the telltale signature of an interstellar origin. The confirmation sent ripples through the astronomical community. This was only the third interstellar object ever detected passing through our solar system. The first, Oumuamua, had shown up in 2017 and sparked intense debate with its cigar-like shape and unexplained acceleration. The second, 2I Borisov, arrived in 2019 and appeared to be a more conventional comet, though it too raised questions about the diversity of objects in interstellar space. Now 3I Atlas was here, and from the beginning, it was clear this visitor would be different from its predecessors. Speed was the first clue to its origin. 3I Atlas was barreling through space at roughly 130,000 miles per hour relative to the Sun. That's fast, but what really matters is the velocity relative to the local standard of rest, the average motion of stars in our galactic neighborhood. When astronomers calculated this, they found that 3I Atlas was moving at speeds that could only mean one thing. It had been traveling through the galaxy for potentially millions of years before stumbling into our corner of space. The gravitational pull of our Sun had barely altered its course, just enough to curve its path slightly as it swung through the inner solar system. Tracking backward along its trajectory revealed something fascinating. 3I Atlas appeared to have originated from the direction of the constellation Lyra, home to the bright star Vega. Now, that doesn't necessarily mean it came from Vega's planetary system. Interstellar objects travel for so long that pinpointing their exact origin becomes nearly impossible. Stars move, orbits shift, and the galaxy rotates. But the general direction gave scientists a starting point to wonder about the alien stellar system this object once called home. What made 3I Atlas stand out immediately was its activity level. Unlike Oumuamua, which appeared inert and rock-like, 3I Atlas was actively outgassing from the moment it was discovered. A fuzzy cloud of material surrounded it, giving it the classic appearance of a comet. This was initially reassuring to scientists. Finally, an interstellar visitor that behaved like the comets we know and love. But that reassurance wouldn't last long. As more observatories turned their attention to the object, data began pouring in that didn't quite make sense. The Hubble Space Telescope captured images showing a teardrop-shaped dust cocoon trailing behind 3I Atlas, but the structure was far more organized than typical cometary tails. The James Webb Space Telescope analyzed the infrared signature and detected thermal emissions inconsistent with pure ice sublimation. Ground-based spectrographs measured the chemical composition of the outgassing material and found that carbon dioxide dominated, with far less water than expected. The scientific community mobilized quickly. This was a rare opportunity to study material from another star system up close. Observing time on every major telescope was immediately allocated to 3I Atlas. Research teams scrambled to collect as much data as possible before the object completed its flyby and disappeared back into the void. But with each new observation, the mystery deepened rather than resolved. 3I Atlas wasn't following the script. it was rewriting it. When you look at a comet through a spectroscope, you're essentially reading its chemical autobiography. The light reflecting off the gas and dust reveals exactly what elements and molecules are present, telling scientists about the conditions where that comet formed billions of years ago. Most comets show strong signatures of water, methane, ammonia, and simple organic compounds. These are the building blocks you'd expect from the cold, distant regions of a solar system. But when researchers pointed their instruments at 3I Atlas, they got a different story entirely. Carbon dioxide dominated the spectrum, not just present, but absolutely flooding the measurements. For every molecule of water detected, there were dozens of carbon dioxide molecules. This is backwards from what we normally see. Water should be the primary volatile in a comet, especially one that formed in the frigid outer reaches of a planetary system where hydrogen and oxygen are abundant. Carbon dioxide comets aren't unheard of, but they're rare, and they certainly don't come from the icy regions where most comets are born. The composition of 3I Atlas suggested it formed somewhere warmer, somewhere more oxidized, somewhere more like the inner regions of a solar system where rocky planets exist. The cyanide detection added another layer to the mystery. Cyanide compounds are actually common in comets, formed from carbon and nitrogen in the early solar system. But the concentrations in 3I Atlas were off the charts. Some measurements showed cyanide levels 10 times higher than typical comets. This suggested an environment extremely rich in carbon and nitrogen, possibly indicating organic chemistry more complex than the simple ices we usually find. A few researchers have quietly speculated that such high cyanide concentrations could indicate biological activity at some point in the object's history, though this remains highly controversial and unproven. Then there's the nickel vapor. This discovery genuinely shocked the research teams analyzing the data. Nickel is a heavy metal that requires substantial heat to vaporize, far more heat than the distant sunlight at 3I Atlas's position could provide. The current leading theory is that tiny metallic grains embedded in the comet's structure are somehow being heated beyond what solar radiation alone should accomplish. But how? Some unknown process must be generating additional heat within the object. This could be radioactive decay from heavy elements, though that would require concentrations of radioactive materials far beyond what we find in typical solar system bodies. The spectroscopic data also revealed something else unusual. The ratios of different isotopes, particularly carbon and oxygen isotopes, didn't match the patterns we see in our solar system. Every star system has a unique isotopic fingerprint based on the specific mix of elements present when it formed. The isotope ratios in 3I Atlas definitively proved its interstellar origin, but they also hinted at formation conditions quite different from those in our own cosmic neighborhood. Whatever star system birthed this object had a chemical history distinct from our sun's. Scientists began constructing models to explain the chemistry. One scenario suggested 3I Atlas formed in the inner region of its home planetary system, perhaps as part of a protoplanetary disk rich in carbon dioxide. Maybe it was a planetesimal that never quite grew into a full planet, ejected by gravitational interactions with larger worlds. Another model proposed it might be a fragment of a larger body, a piece of a planet that was destroyed in some ancient cataclysm. The carbon dioxide could have been trapped in the rocks, slowly released over billions of years as the fragment tumbled through space. But some researchers started proposing more exotic explanations. What if 3I Atlas formed around a different type of star, perhaps a cooler red dwarf where the habitable zone sits closer to the star? In such a system, carbon dioxide might be more abundant than water in certain regions. Or what if it came from a system with a different chemical composition entirely, one enriched in carbon and oxygen but depleted in hydrogen? These scenarios push the boundaries of our understanding, but might be necessary to explain what we're seeing. The debate over 3I Atlas's composition has exposed just how little we truly understand about the diversity of objects in our galaxy. We've studied comets and asteroids in our own solar system for centuries, but those are all siblings, born from the same parental cloud of gas and dust. Interstellar visitors like 3I Atlas give us our first glimpses of how planetary systems form elsewhere, under different conditions, around different types of stars. And what we're learning is that the universe is far more varied and strange than our single solar system ever suggested. In the world of astrophysics, few names spark as much debate as Avi Loeb. The Harvard professor and former chair of the astronomy department has built a reputation for asking uncomfortable questions about interstellar objects. When Oumuamua accelerated away from the sun without any visible outgassing to explain the push, most scientists attributed it to subtle effects they couldn't quite detect. Loeb suggested it might be a light sail, possibly of artificial origin. The backlash from the scientific community was swift and harsh, yet Loeb doubled down, arguing that scientists have a responsibility to consider all possibilities, no matter how extraordinary. Now, with 3I Atlas making its dramatic flyby of Mars, Loeb is once again raising the possibility of artificial origins. But this time, his arguments are drawing more attention and less immediate dismissal. The difference is data. With Oumuamua, scientists were playing catch-up, scrambling to observe an object already leaving the solar system. With 3i Atlas, we've had months of detailed observations, and the data keeps revealing anomalies that challenge natural explanations. Loeb's primary concern centers on the mass calculations. The outgassing rates observed from 3i Atlas, combined with its brightness and thermal emissions, should allow scientists to estimate its size and mass fairly accurately. These calculations rely on well-established physics that's been validated on thousands of comets. But when researchers run the numbers for 3i Atlas, something doesn't add up. The object appears to be far more massive than its outgassing behavior suggests it should be. It's losing carbon dioxide at rates consistent with a relatively small icy body, yet gravitational measurements indicate something much larger and denser lurks beneath that dusty exterior. This discrepancy has led Loeb to propose a radical idea. What if 3i Atlas isn't a solid chunk of ice and rock, but rather a hollow or partially hollow structure? A natural comet forms through accretion, with material gradually building up layer by layer. This process creates a relatively uniform density, but an artificial object could be constructed with internal voids, giving it a much larger volume for a given mass, or conversely, a much greater mass for its apparent size. The latter scenario would explain why 3i Atlas appears so massive despite modest outgassing rates. In a recent paper, Loeb outlined several other characteristics that he finds suspicious. The trajectory through the solar system, while not impossible for a natural object, is remarkably well positioned to allow close observation by both Earth-based telescopes and Martian orbiters. The timing of its arrival, coinciding with advanced space telescope capabilities like Webb and SPHEREX becoming operational, maximizes our ability to study it. The electromagnetic emissions detected during the Mars flyby, though weak, show patterns that some argue are more structured than random noise would produce. Loeb is careful to state he's not claiming 3i Atlas is definitely artificial. Rather, he's arguing that the scientific method demands we consider this hypothesis alongside natural explanations. The problem, he contends, is that the astronomical community has developed a cultural bias against even discussing artificial origins for celestial objects. This bias, he suggests, could blind us to evidence right in front of our instruments. History is full of examples where scientists missed obvious explanations because they fell outside the accepted paradigm. Loeb worries we might be repeating that mistake. The reaction from other scientists has been mixed. Many dismiss Loeb's suggestions as attention-seeking speculation that undermines serious astronomical research. They point out that extraordinary claims require extraordinary evidence, and the anomalies he highlights can likely be explained with more conventional physics once we gather enough data. Comets are complex objects, and our models are still imperfect. Just because we don't fully understand something doesn't mean we should jump to alien explanations. But a minority of researchers admit, often off the record, that Loeb raises valid points worth investigating. The coincidences are piling up. The Mars flyby, the unusual composition, the anomalous mass, the unexplained emissions. Each individual piece might have a natural explanation, but collectively, they form a pattern that deserves scrutiny. Several scientists have called for the creation of a systematic protocol for evaluating potential technosignatures in interstellar objects, a set of criteria that would allow objective assessment without the stigma currently attached to such discussions. Whatever 3i Atlas turns out to be, the scientific community wasn't about to let this opportunity slip away. The moment its interstellar origin was confirmed, space agencies around the world began coordinating an unprecedented observation campaign. This would be the most thoroughly studied interstellar visitor in history, examined by a fleet of spacecraft and telescopes representing humanity's most advanced astronomical capabilities. Leading the charge was NASA's Hubble Space Telescope, which had previously captured stunning images of 2I Borisov. Hubble's observations of 3i Atlas began in August and continued through its closest approach to Mars. The telescope's sensitive cameras captured the evolving dust cocoon in exquisite detail, revealing structure and dynamics that ground-based observatories couldn't resolve. The images showed material streaming off the object in jets, but the jets were coming from specific locations on the surface rather than uniformly, suggesting either rotation with active regions or possibly discrete vents expelling material. The James Webb Space Telescope brought its infrared capabilities to bear, peering through the dust to analyze the thermal emissions and chemical composition with unprecedented precision. Webb spectrographs broke down the light into thousands of individual wavelengths, allowing researchers to identify even trace compounds in the outgassing material. The telescope detected complex organic molecules, including formaldehyde and methanol, alongside the dominant carbon dioxide. These organics weren't surprising in themselves, but their abundance ratios suggested chemical processing under conditions different from our solar system's formation. SPHEREX, NASA's newest space-based observatory, designed to map the entire sky in infrared light, contributed continuous monitoring data. Unlike telescopes that observe specific targets for limited periods, SPHEREX's all-sky survey approach meant it could track 3i Atlas over extended periods, documenting any changes in brightness, color, or activity level. This continuous coverage proved invaluable when the object exhibited a sudden brightening event in mid-September that lasted only 18 hours. Without SPHEREX's vigilant watch, that event might have been missed entirely. But the real coup came from the Mars orbiters. ESA's Mars Express and ExoMars Trace Gas Orbiter were perfectly positioned to observe 3I Atlas during its closest approach to the red planet. This was unprecedented. Never before had we been able to study an interstellar object with spacecraft located at a different vantage point than Earth. The Martian orbiters could measure the object's properties from a completely different angle, providing stereoscopic data that revealed its three-dimensional structure and rotation. The Mars Express observations detected something unexpected. As 3I Atlas passed nearest to Mars, instruments recorded a brief spike in electromagnetic activity on frequencies commonly associated with plasma interactions. The signal was weak but distinct, lasting approximately 47 minutes during closest approach. Some researchers have proposed this was caused by 3I Atlas's outgassing material interacting with Mars's thin magnetosphere, creating a temporary disturbance in the charged particle environment. Others find this explanation insufficient and suggest the electromagnetic signature might originate from within the object itself. Ground-based observatories coordinated their observations to fill gaps when space telescopes were unavailable. Radio telescopes listened for any electromagnetic emissions across a wide range of frequencies. Optical telescopes with adaptive optics systems captured high-resolution images during the brief windows when atmospheric conditions permitted. Even amateur astronomers with backyard telescopes contributed observations, tracking the object's position and brightness to help refine orbital calculations. The coordination required for this observation campaign was staggering. Scientists had to carefully schedule telescope time, ensuring that different instruments observed the object at optimal moments to capture complementary data. International collaboration was essential, with research teams in the United States, Europe, Asia, and Australia working together to piece together a comprehensive picture. The sheer volume of data generated has kept hundreds of researchers busy with analysis, and new findings continue to emerge from observations made months ago. Despite this unprecedented observation effort, critical questions remain unanswered. The core of 3I Atlas remains hidden beneath layers of dust and gas, its true structure a mystery. The exact mass is still uncertain, with estimates varying by factors of 2 or more depending on which model assumptions researchers use. The source of the unexplained heat generating the nickel vapor hasn't been identified, and those electromagnetic emissions recorded by Mars Express, scientists are still debating whether they represent a natural phenomenon or something that requires a different explanation entirely. Orbital mechanics is one of the most precise sciences we have. Give astronomers an object's position, velocity, and the gravitational influences acting on it, and they can predict its path with extraordinary accuracy. Comets, asteroids, planets, they all follow trajectories governed by Newton's laws and Einstein's general relativity. The universe is predictable, orderly. At least, it's supposed to be. But 3I Atlas has been testing those assumptions in ways that make orbital dynamicists deeply uncomfortable. The trajectory itself, on paper, looks unremarkable. A hyperbolic orbit carrying the object through the inner solar system, curving around the sun, then back out toward interstellar space. Standard physics, but look closer at the specific path, and patterns emerge that seem almost too convenient. The object's trajectory brought it within optimal viewing distance of Mars at exactly the moment when Earth-based telescopes and Martian orbiters could observe it simultaneously. If you were planning an interstellar flyby mission and wanted to maximize scientific observation opportunities, you'd be hard-pressed to design a better trajectory. The Mars encounter distance of roughly 30 million kilometers represents a sweet spot. Close enough that spacecraft instruments can gather detailed data, far enough that there's no risk of gravitational perturbations significantly altering the object's course. Pure coincidence? Possibly. But astronomers have calculated the statistical probability of a random interstellar object passing this close to Mars, and the numbers aren't reassuring. Given the vast emptiness of space and the relative positions of the planets, the odds work out to something like 1 in several thousand that an interstellar visitor would happen to pass within this distance of Mars. Then there's the timing relative to the object's perihelion, its closest approach to the Sun. 3I Atlas reached perihelion in late October, but here's where things get interesting. At that exact moment, the Sun was positioned between Earth and the object from our perspective. The geometry meant that 3I Atlas passed through its closest approach to our star while completely hidden from Earth's view, blocked by the Sun's blinding glare. For several critical weeks, as the object experienced maximum heating and activity, we couldn't observe it directly. This might seem like bad luck, but it's incredibly convenient if you're an interstellar object trying to avoid scrutiny. During perihelion, any anomalies in the object's behavior would be most apparent. If 3I Atlas is artificial or contains artificial components, that would be when thermal stresses might reveal internal structures or when power systems might show unusual signatures. Yet that's precisely when observations from Earth became impossible. By the time the object emerged from behind the Sun, any evidence of unusual perihelion behavior had already faded. Some researchers have pointed out another curious aspect of the trajectory. The plane of 3I Atlas's orbit is nearly aligned with the ecliptic. the plane in which most planets orbit the Sun. Interstellar objects can approach from any angle, and statistically, most should have orbital planes significantly tilted relative to the ecliptic. Yet 3I Atlas came in at a relatively shallow angle, almost as if it were following the same plane as the planets. This made it easier to detect and track, but it's geometrically unusual for a random visitor from interstellar space. The velocity presents its own puzzle. At 130,000 miles per hour relative to the Sun, 3I Atlas is moving fast, but not extraordinarily so for an interstellar object. What's interesting is that this speed places it in a narrow range that maximizes observation time while still clearly indicating interstellar origin. Much faster, and the object would zip through the solar system too quickly for detailed study. Much slower, and its interstellar nature would be less certain, possibly mistaken for a solar system object on an unusual orbit. The velocity seems optimized for a slow, observable flyby. Skeptics correctly point out that we're dealing with small number statistics here. With only 3 confirmed interstellar objects ever detected, we don't have enough data to know what's typical and what's anomalous. Maybe trajectories like 3I Atlases are actually common, and we're just seeing patterns where none exist. Our detection methods are biased toward finding objects on certain types of orbits, so the sample we have isn't necessarily representative of all interstellar visitors. These are valid criticisms that any rigorous analysis must acknowledge, yet the coincidences keep accumulating. The Mars flyby at optimal distance, the perihelion hidden behind the Sun, the ecliptic-aligned orbital plane, the perfectly paced velocity. Individually, each could be random chance. Together, they create a trajectory that looks suspiciously well designed for observation, while maintaining plausible deniability of artificial origin. Either we're witnessing an extraordinarily unlikely series of coincidences, or 3I Atlas's path through our solar system was influenced by something more than just gravity and momentum. Beyond the trajectory and composition, 3I Atlas has exhibited behaviors that continue to puzzle researchers. These aren't just measurement uncertainties or modeling limitations. They're observational facts that don't fit neatly into our understanding of how comets work, even exotic interstellar comets from alien star systems. The most significant anomaly is what astronomers call non-gravitational acceleration. When a comet releases gas, the escaping material acts like tiny rocket thrusters, giving the comet a small push. This effect is well understood and can be calculated based on how much gas is escaping and in which direction. For 3I Atlas, scientists measured the outgassing rates and predicted how much the object's trajectory should change, but the actual trajectory didn't match the prediction. The object experienced acceleration that's either too strong or too weak, depending on which model assumptions you use, but definitely different from what the outgassing alone should produce. This is particularly troubling because it was the same type of anomaly that made Oumuamua so controversial. That object accelerated without any visible outgassing, leading to all sorts of speculation. With 3I Atlas, we can see the outgassing clearly, so we should be able to nail down the cause of any acceleration. Yet the numbers still don't balance. Either there's outgassing we can't detect, perhaps from the night side of the object, or some other force is acting on it. Proposals have included magnetic effects, radiation pressure on dust grains, or even tidal forces from the Sun, but none fully account for the discrepancy. The sudden brightening event captured by Spherex in September added another mystery. For roughly 18 hours, 3I Atlas became noticeably brighter, increasing its luminosity by almost 30% before returning to baseline levels. Comets do sometimes exhibit outbursts where they suddenly release large amounts of material, temporarily brightening. But those events usually last days or weeks, and are associated with clear increases in outgassing. The 3I Atlas brightening was brief, and showed no corresponding spike in carbon dioxide or dust production. Something made the object brighter without significantly increasing its mass loss. Temperature measurements have also yielded confusing results. The object should be heating up as it approaches the Sun, and cooling as it moves away, following predictable thermal curves based on solar distance. And to a large extent, 3I Atlas does follow these predictions. But there are deviations. The object appears slightly warmer than it should be at its current distance from the Sun, suggesting an internal heat source beyond just absorbed sunlight. The temperature difference isn't huge, maybe 20 or 30 degrees Kelvin, but it's consistent and measurable across multiple observations. This excess heat could explain the nickel vapor problem. If something inside 3I Atlas is generating warmth, perhaps radioactive decay of heavy elements, that could create hotspots on the surface where metallic grains reach vaporization temperatures. But this raises new questions. Natural comets don't typically contain significant amounts of radioactive materials. Where would 3I Atlas have acquired them? Are we looking at a fragment of a destroyed planet's core, where heavy elements would have concentrated? Or is this evidence of something even more exotic? The rotation rate presents yet another puzzle. Most comets spin, tumbling through space as they orbit. The rotation rate can be determined by watching how brightness varies as different surfaces face Earth. For 3I Atlas, attempts to measure rotation have yielded inconsistent results. Some observations suggest a rotation period of about 9 hours. Others find evidence for a much slower rotation, maybe 20 hours or more. A few researchers have proposed the object might be in a complex tumbling state, rotating around multiple axes simultaneously. But this doesn't fully explain the data either. Perhaps most intriguingly, there's the issue of the electromagnetic emissions detected during the Mars flyby. The signal recorded by Mars Express lasted 47 minutes and showed distinct peaks at regular intervals, roughly every 8 minutes. Natural plasma interactions don't typically produce such regular patterns. Radio bursts from astronomical sources are usually either continuous or random. Structured, repeating signals generally indicate some kind of oscillating or rotating source. What could be oscillating inside or around 3I Atlas with such precise timing? Scientists have proposed various explanations. Maybe the object's irregular shape creates vortices in the outgassing material, and these vortices generate electromagnetic effects as charged particles spiral. Perhaps the rotation brings active regions into and out of sunlight, creating a day-night cycle that affects plasma production. There could be magnetic field lines connecting to the solar wind, and the object's motion through these fields generate electromagnetic induction. All plausible ideas, but none have been definitively confirmed. The cumulative effect of these anomalies is growing scientific unease. Each individual mystery might have a conventional explanation, but finding conventional explanations for all of them simultaneously is becoming increasingly difficult. The picture emerging from months of intensive observation is of an object that refuses to fit our established understanding of comets. Either we need to fundamentally revise our models of cometary physics, or we need to consider that 3I Atlas might not be a typical comet at all. The scientific debate over 3I Atlas has evolved into two main camps, each with compelling arguments, and each acutely aware of the extraordinary implications of their position. On one side are researchers who insist that, despite the anomalies, 3I Atlas must be a natural object because artificial explanations require assumptions even more extreme than the mysteries they're trying to solve. On the other side are scientists willing to at least consider that some of the object's characteristics might indicate artificial origins or modifications, arguing that ruling out such possibilities without investigation is itself unscientific. The natural camp points to a fundamental principle. We've only detected 3 interstellar objects ever. That's an absurdly small sample size. With such limited data, we can't possibly know what's typical and what's unusual for objects traveling between star systems. Maybe carbon dioxide-rich composition is common for interstellar comets. Maybe anomalously massive objects are ejected frequently from other planetary systems. Maybe the trajectory patterns we're seeing are actually statistically normal, and we just don't have enough experience to recognize it yet. These researchers emphasize that comets are inherently complex and poorly understood, even within our own solar system. We've sent spacecraft to visit only a handful of comets up close, and each one revealed surprises that challenged existing theories. Comet 67P, studied extensively by the Rosetta mission, had a bizarre rubber duck shape and outgassing behaviors that no one predicted. Comet Borisov, the previous interstellar visitor, showed carbon monoxide concentrations 27 times higher than typical solar system comets. The universe is weird. Objects from other star systems are going to be weirder. That doesn't mean they're artificial. The natural explanation advocates also point out the danger of jumping to extraordinary conclusions based on incomplete data. History is full of astronomical phenomena that seemed inexplicable until better observations or theoretical advances provided conventional explanations. Pulsars were initially jokingly called little green men because their precise radio pulses seemed almost artificial. Fast radio bursts baffled astronomers for years before natural mechanisms were identified. Jumping straight to "it's aliens" without exhausting all natural possibilities is bad science and damages credibility. Furthermore, the natural camp argues that the engineering challenges of creating an artificial object like 3I Atlas would be staggering. We're talking about something with a mass of 33 billion tons traveling through interstellar space for potentially millions of years. The energy required to accelerate such an object to interstellar velocities would be astronomical, far beyond anything our own civilization could contemplate. And for what purpose? If an advanced civilization wanted to explore our solar system, why send something so massive and so obviously comet-like? It doesn't make sense from an engineering or mission design perspective. On the other side of the debate are researchers who argue that dismissing artificial possibilities prematurely is itself a form of bias. They point out that the scientific method requires considering all hypotheses that fit the observations, then using evidence to eliminate incorrect ones. Ruling out artificial origins from the start, simply because they seem unlikely or uncomfortable, violates this principle. If the data suggests something unusual, we have an obligation to investigate rather than assume it must fit existing natural models. These scientists emphasize the accumulation of coincidences. Yes, individually each anomaly might have a natural explanation, but how many coincidences do we need before the natural explanation becomes more contrived than the artificial one? The Mars flyby perfectly timed for observation. The carbon dioxide composition matching Mars's atmosphere. The anomalous mass that defies comet formation models. The electromagnetic emissions with structured patterns. The trajectory that maximizes viewing opportunities while hiding during perihelion. At what point does Occam's razor start favoring the simpler explanation that something about this object is intentional? Proponents of investigating artificial origins also challenge the engineering objection. We're assuming any alien technology would be limited by the same constraints we face, but a civilization millions of years more advanced than us might have capabilities we can't even imagine. What seems impossible to us, accelerating 33 billion tons to interstellar speeds, might be routine for a sufficiently advanced society, and maybe the purpose isn't exploration in the way we conceive it. Perhaps it's a probe designed to study multiple star systems over millions of years, deliberately massive to survive the journey, and equipped to investigate interesting targets like Mars. Some researchers have proposed a middle ground. What if 3I Atlas is primarily natural, but has been modified or influenced by artificial means? Perhaps it's a captured comet that was used as an interstellar transport, its natural outgassing providing cover for artificial components hidden within. Or maybe it's debris from some ancient space infrastructure, a fragment of a megastructure or space station that was destroyed long ago. These hybrid scenarios could explain both the natural comet-like features and the anomalous characteristics that don't quite fit. The debate has also sparked discussion about detection strategies. If interstellar objects could potentially be artificial, how would we recognize them? What signatures should we be looking for? Some scientists have called for establishing formal protocols, a checklist of observations and tests that could help distinguish between natural and artificial origins. This wouldn't assume any particular object is artificial, but would ensure we don't miss evidence through lack of systematic investigation. One challenge is that any criteria we establish might be too narrow, reflecting our own technological assumptions rather than the possibilities of truly alien engineering. An artificial object designed by non-human intelligence might not look anything like our probes and satellites. It might use materials, energy sources, and operating principles completely foreign to our experience. How do you create a detection protocol for something you can't even imagine? The tension between these camps reflects a deeper question about how science approaches the unknown. Do we stick with established frameworks and conventional explanations until they're definitively proven wrong, or do we embrace uncertainty and actively investigate unconventional possibilities? Both approaches have merit, and the truth probably lies somewhere in between. What's clear is that 3I Atlas has forced this conversation to the forefront of astronomy in a way that previous interstellar visitors didn't quite manage. As of early November 2025, 3I Atlas is moving away from the Sun and beginning its long journey back to interstellar space. The intense observation campaign has wound down, not because scientists have lost interest, but because the object is rapidly becoming too faint and too distant for detailed study. Within a few months, it will fade below the detection threshold of even our most powerful telescopes, and then it will be gone, disappearing into the cosmic void from which it came, leaving behind more questions than answers. The data collected during its flyby represents the most comprehensive examination of an interstellar object ever conducted. Thousands of observations from dozens of instruments have generated petabytes of information. Research teams will be analyzing this data for years, searching for subtle patterns and correlations that might resolve some of the mysteries. Papers are already being published, with more in the peer review pipeline. The scientific legacy of 3I Atlas will extend far beyond its brief visit, but some of the most critical observations will never be made. The passage behind the Sun meant we missed what could have been the most revealing phase of its journey. Whatever happened during perihelion, when the object experienced maximum heating and stress, remains hidden. If there were internal structures to be revealed, thermal anomalies to be detected, or behavioral changes to be documented, that opportunity has passed. The timing of that solar occultation remains one of the most frustrating coincidences of the entire encounter. Scientists have begun discussing plans for future interstellar visitor studies. 3I Atlas has exposed gaps in our observational capabilities and highlighted the need for better coordination between different observatories. There's talk of establishing a rapid response network, a system that could mobilize global resources within hours of detecting a new interstellar object. The goal would be to maximize data collection before the visitor passes through the solar system and vanishes forever. Some researchers have proposed even more ambitious ideas. Could we send a spacecraft to intercept a future interstellar visitor? The mission would be extraordinarily challenging, requiring launch within days of detection and enormous delta-v to match velocities with an object moving at 130,000 miles per hour. But it's theoretically possible, especially if we had spacecraft on standby, fueled and ready to launch on short notice. A close flyby, or even a sample return mission, could answer definitively whether these objects are natural, artificial, or something in between. The Mars connection continues to fascinate researchers. The fact that 3I Atlas passed so close to a planet with an atmosphere dominated by the same carbon dioxide found in the comet seems less like coincidence the more you think about it. Some scientists have speculated that if the object is artificial, Mars might have been the intended target for closer study. Perhaps ancient civilizations once thrived on Mars before the planet lost its thick atmosphere, and 3I Atlas is a probe investigating the fate of those civilizations. It's pure speculation, but it's the kind of speculation that 3I Atlas invites. What makes this particular interstellar visitor so significant is that it challenges our assumptions about what's possible. Before Oumuamua, most astronomers assumed interstellar objects passing through our solar system would be rare events we'd never detect. Now we've found 3 in 8 years, suggesting such visitors might be relatively common. Before 3I Atlas, we assumed interstellar comets would resemble solar system comets in composition and behavior. That assumption has been thoroughly shattered. Each new discovery forces us to expand our understanding of the universe's diversity. The unanswered questions are profound. Where exactly did 3I Atlas originate? What star system birthed this object, and under what conditions? If it's a planetary fragment, what cataclysm destroyed the parent world? How long has it been traveling through the galaxy, and what other star systems might it have visited before reaching ours? These questions may never be answered with certainty, but they drive imagination and scientific inquiry in equal measure. Perhaps most importantly, 3I Atlas has demonstrated that we live in a dynamic galaxy where material regularly moves between star systems. Comets, asteroids, possibly even life-bearing rocks are ejected from their home worlds and wander the interstellar void, occasionally stumbling into alien solar systems like ours. This means that the chemistry, and perhaps even the biology, of distant star systems might arrive at our doorstep for study. Every interstellar visitor is a cosmic gift, a sample of another world delivered to us without the need for expensive interstellar missions. The debate over whether 3I Atlas could be artificial will likely continue for years, possibly decades. Without definitive proof either way, both camps will maintain their positions, each finding evidence to support their interpretation in the available data. This ambiguity might actually be healthy for science, keeping minds open to possibilities and driving more rigorous observation and analysis. The worst outcome would be premature consensus before all the evidence is properly examined. As 3I Atlas fades from view, astronomers are already watching for the next interstellar visitor. With improved detection systems and heightened awareness, the next one might be spotted even earlier, allowing for longer observation periods and better data collection. Each visitor teaches us something new, each one challenges our theories, and each one reminds us that we're part of a vast cosmic ecosystem, where objects routinely cross the boundaries between star systems. The Mars flyby on October 3rd will be remembered as a landmark moment in astronomy. Never before had an interstellar object passed so close to another planet while under such intensive observation. The data collected during those hours, particularly the electromagnetic emissions detected by Mars Express, will be scrutinized for years to come. Whether those emissions represent natural plasma physics or something more exotic remains an open question, one that may define how we think about interstellar objects for decades. In the end, 3I Atlas leaves us with a humbling realization. The universe is full of surprises, full of objects and phenomena that don't fit our neat categories and established theories. Every time we think we understand how things work, something like 3I Atlas comes along to remind us how much we still don't know. That's not a weakness of science, but its greatest strength, the willingness to be surprised, to update our models when confronted with new evidence, to ask uncomfortable questions even when the answers might challenge our worldview. So what is 3I Atlas really? Is it a natural comet from another star system, formed under exotic conditions we've never encountered before? Is it a planetary fragment, a piece of an alien world destroyed in some ancient catastrophe? Or could it possibly be something artificial, a probe or artifact from a civilization we can't even imagine? The honest answer is that we don't know for certain. We may never know for certain. But the quest to find out, the investigation itself, has already expanded our understanding and pushed the boundaries of human knowledge. One thing is clear. The coincidences are too numerous to ignore. The Mars flyby at optimal distance with matching atmospheric chemistry, the anomalous mass that defies explanation, the electromagnetic patterns that suggest structure rather than randomness, the trajectory that maximizes observation while hiding during critical moments. Each piece might be explicable individually, but together they paint a picture of an object that's anything but ordinary. As 3I Atlas disappears into the darkness between stars, it carries with it the secrets of its origin and purpose. But it leaves behind a transformed field of astronomy, one more willing to question assumptions and consider possibilities that would have been dismissed just years ago. And somewhere out there in the galaxy, other interstellar travelers are making their way toward our solar system, each carrying their own mysteries, each ready to challenge what we think we know about the universe. The next visitor could arrive next month, next year, or next decade. When it does, we'll be watching, And maybe, just maybe, that visitor will provide the answers that 3I Atlas kept hidden. Until then, we're left with one of the most intriguing mysteries in modern astronomy, an object that came from the stars, passed by Mars in a way that seems almost too perfect to be random, and vanished back into the cosmos before revealing its true nature. The Mars encounter wasn't a coincidence. The evidence suggests something deeper, something we're only beginning to understand. Whether that something is exotic natural physics or artificial design, the universe has shown us that reality is stranger and more fascinating than we ever imagined. And 3I Atlas, whatever it truly is, has ensured that we'll never look at interstellar visitors the same way again.